Okay, moving on to chapter 15. Had a little bit of false start there in my first attempt at the video, so I've got a little bit written in here already, but that will maybe help me get through it a little more quickly so I don't have to break the video for different pages. One thing to point out before we get started here, these note outlines I'm using were designed for work with a computer and a projector or a smartboard. So there's a couple places, particularly in this chapter, where I didn't leave a whole lot of space to work out the problem, right? Which often on a smartboard, I've got bigger margins where I can put things. So you might want to just have a blank piece of paper to maybe take some additional notes here and there as you go through. So just be aware of that. Okay, so back in chapter 4, we did talk about acids and bases, and in particular we talked about acid-base reaction. Acid plus base gives water, and then a salt of the leftover pieces. That generally is considered the Arrhenius definition of an acid and a base. Acid making H plus in solution, base making hydroxide ion or OH minus in solution, and then H plus OH minus gives you water, would be your net ionic equation for the acid-base reaction. What we want to look at here is kind of a more encompassing definition that's very useful for reactions that happen in aqueous solution, and that's called the Bronsted-Lowry definition of acids and bases. And in the Bronsted-Lowry definition, an acid donates H plus in solution. Now, H plus is usually read as proton, so this would be donates protons in solution, because if you take a hydrogen atom and remove its electron, all that's left is the single proton in the nucleus. And a base in the Bronsted-Lowry definition has sort of a complementary definition. A base is something that accepts H plus in solution. So an acid-base reaction under this definition is really this H plus, or this proton, moving back and forth between two species, one that we'll call the acid, one that we'll call the base. Now that we've talked about equilibrium, we may recognize the fact that some reactions go completely in one direction, and some reactions go in both directions. This is going to be true for acids and bases as well. And this gives us two kind of broad categories for acids and bases. Some acids and bases will be classified as strong acids or bases. These are the ones that completely dissociate in aqueous solution, so this would be your one-way reaction. And it's important for us to recognize the strong acids and bases, because if we recognize strong acids and bases, then any other acid or base we might recognize would be a weak acid or base, and we would know that we need to use an equilibrium approach to those particular types of problems. So the strong acids are HCl, hydrochloric acid, HBr, hydrobromic acid, HI, which in aqueous solution would be hydroiodic acid, says hi by the way, nitric acid, HNO3, H2SO4, which would be sulfuric acid, and HClO4, which is perchloric acid. So 6, right? And the textbook we're using, many textbooks will leave it there at 6. I think it's important to recognize that this is actually kind of a continuum of acid strength. Some cases you'll see chloric acid, HClO3, listed as a strong acid as well. It kind of depends where you look. So kind of here in the age of the internet, where you're looking at different sources of information, you may see that one lumped in as a strong acid. Any other compound that has a proton that could be donated will be a weak acid. Now, lots of acids are written so that the first hydrogen in the formula is the acidic proton. This is generally true for what are called inorganic acids. Organic acids, if you ever see something like that, CO2H, and this is usually at the end, so there's more of the compound here. I'll use R just for an abbreviation. More of the compound here, but this is a functional group called a carboxylic acid. So we see this at the end of a formula. That's also an acidic proton right there, and that would be an acid. Now, the strong bases, we really did learn back in chapter 4. Strong bases are completely soluble hydroxides, metal hydroxides. So that would be the first row of the periodic table. So that would be lithium hydroxide, sodium hydroxide, potassium hydroxide. A lot less likely, but rubidium hydroxide and cesium hydroxide as well. Right, rubidium and cesium just very rare and expensive. You wouldn't use them just as a hydroxide base very often. But in an example problem, they could certainly pop up. So that's the first column of the periodic table, the alkali metals. And then the larger metals of the second column, barium hydroxide, strontium hydroxide, and calcium hydroxide, are also classified as strong bases. And there's some leeway on this end too. I've seen some textbooks that don't count calcium hydroxide or strontium hydroxide as strong bases, because you're kind of getting to a point on that continuum where you have to choose to draw a line sometimes and say, yep, I'm going to call this one a strong base. But in our textbook, those are all considered strong bases. Now, any other base is going to be a weak base. So any other metal hydroxide is only partially soluble or partially ionized. Those will be weak bases. But in reality, if an atom has a lone pair of electrons, it can act as a base, because you can use that lone pair to make a bond to the H plus or to the proton. So a lot of compounds like phosphorus and nitrogen compounds are commonly reactive as bases because of that lone pair on the nitrogen or on the phosphorus. It's helpful to look for negative charges as well. If something has a negative charge, that is generally an indication that it's got an extra lone pair of electrons that it can use to make that bond. Now, I mentioned there is a reciprocal relationship back here in terms of the definitions, and that leads to an idea that's important here that we recognize, that acids and bases can be conjugates of each other. So let's take a fairly simple formula-wise weak acid, HF or hydrofluoric acid. If it's in aqueous solution, so it's an acid. If it's in aqueous solution, what's going to happen is it's going to react with the water that surrounds it. So water would be pure liquid in this case. And it will establish an equilibrium, right? Since it's a weak acid, there'll be an equilibrium that governs what's going on here. Being an acid, what it does is it donates a proton. So HF is going to donate a proton, and that proton is going to end up with the water. So that means we'll get H3O+. H3O+ is called hydronium ion. That would be aqueous because it's surrounded by the water. The proton and the positive charge gone would leave F- here on the product side, also in aqueous solution. Now, if HF is the acid, that means water in this case is the base. HF's donating a proton, water's accepting a proton. Over here, now the water's been protonated to hydronium. On this side of the equation, this is the acid. So this is what we refer to as the conjugate. Let me write it all the way out here for the first time. Conjugate acid. And what that means is if the reaction goes backwards, this would be the acid. This is what's donating the proton. That makes F- here the conjugate base, because in the backward reaction, it would be accepting a proton to reform the weak acid. So here's this reciprocal relationship between HF and F-, acid, conjugate base, base, conjugate acid, between water and hydronium. Now, we get a similar kind of set of equations, or a similar equation and set of relationships if we just look at a base. So ammonia, if it's aqueous, is a base. Right? We said just a minute ago about having a lone pair. There's a lone pair in that nitrogen that can accept the proton. If this goes into aqueous solution, water in this case will act as the acid. So proton is transferred from water to the base. That would give us NH4+ or ammonium cation. That's the conjugate acid in this particular case. Right? And now the water lost an H+, that leaves it as hydroxide ion. Hydroxide in this case would be referred to as the conjugate base. So again, the base has this sort of related acid form on the other side of the equation, and the acid has this related base form on the other side of the equation. Okay, I'm going to pause there and do another video for the rest of the page.